I hope, now it works, that you can hear me, even in Kazan.
Yeah, teacher.
How is the sound quality in Kazan?
Yeah, pretty good.
Ja. You can speak. Es spricht Ruslan. Ruslan is calling, but I can't hear him.
I said sound is pretty good.
Ruslan. Ruslan, can you speak? Is it possible?
Yes, I can.
So I hope you can hear me. Otherwise, you have to write in the chat that you can't hear me, okay? Okay. So now, sorry for the short delay. What have we done in the last lecture? So we introduced the entropy, as you remember, after just talking about basics of stochastic. So we introduced the entropy, let's say, as an, where is it? Basics of stochastic. It's here, yeah. We introduced the entropy, let's say, as an expected value of the information content of a random variable. So, and until now, we only talk about discrete random variables. And then we even introduced the joint entropy in the last lecture and even in the seminar. And we already discussed the so-called Venn diagram, which is shown here. And according to the Venn diagram, it's easy to understand the concept of joint entropy, as you can see here. So if you have a random variable x, and if you have a random variable y, yeah, both have a certain entropy, but let's say the surprise in x and y may be lower than the surprise in x plus y, and x separately and y separately, because x and y can be statistically dependent. And we had a nice example, in my opinion, where we said if we know y in this example, we also know x. So this means the mutual information h of x comma y, which means here this red area, yeah, can't be larger in this example than the entropy of y. But in this example, of course, h of y was larger than h of x. Here is just the opposite. Then we said we can identify even more areas. And let's say we take a look at this blue area. Yeah? And if we add the blue area to the green area, then we end up in basically the red area. You have to think about, let's say, that this area is marked. So this means, according to this figure, if you want to express the joint entropy, we can say this joint entropy is the entropy of x plus the conditional entropy of y given x. So if you know x, what is the surprise in y? It makes sense, okay? That this diagram is valid, but we have to prove this. We do this, yeah? And of course, you could also say the joint entropy of x and y. So the red area is the same as the entropy in y. So this would be black circle here, or black area, not shown, yeah? So it's this black area plus, let's say, this area here, which goes from here to here. It's not shown. And this would be h of x given y. So y, is there a surprise in x? Yeah? And if both random variables would be statistically independent, then basically this area here of x, maybe I switch this off here, would not overlap, yeah, with this area of x. That's clear. So now we can proceed. And what we basically want to show is that the joint entropy, if you write the joint entropy, here's the joint entropy, yeah, that we can really write this joint entropy as the entropy of X, for instance, plus the entropy of Y given X. And we start with the joint probabilities and substitute the joint probabilities by the conditional probabilities. And then we should end up in this equation here, yeah, for the conditional entropy. But we start here because this was not new, as you have seen, the joint entropy. So we said, if you know the definition of an entropy, here's the definition of entropy. Yeah? It only depends on the probability, the probabilities of the random variable. And then if we have a joint random variable, let's say x, y, there's no new method required because we can say this is a two-dimensional random variable, let's say set. And then we take a look at all probabilities of this set and weight the information content of this set values measured by means of the dual logarithm of the probability here by the probabilities. And this is just the joint entropy. Yeah? But we can write this joint entropy by means of the conditional entropy. So we want to show this equation. And then we take a look, a final look at this area here, this area, and this small area, which looks like an eye in this diagram, yeah, but vertically aligned, 90 degrees aligned. And this is called the so-called mutual information. So this black area is the mutual information. And this is basically the information, as the name says, yeah, which is both an X and Y. So which is basically shared between X and Y. Yeah, this is a mutual information. Later we use this mutual information to derive the channel capacity of a certain given channel. We start with discrete channels and then we later take a look at continuous channels. Okay, so that's all for now. Now, as I said, we want to prove that we can express the joint entropy by means of a given entropy plus the conditional entropy. This is what we want to show. Okay, this is where we start now. So, so we continue with the last lecture, yeah, and say prove that h of x, comma y, so the joint entropy is equal to, let's say, I mean, there are two possibilities, but I want to show that this is equal to h of x plus h of y given x. And we just start with our knowledge. So we say h of x and y is nothing else than sum. So we consider all possible combinations of the realizations x and y. So we take a look at all x. We take a look at all y, let's say. And it's good to put here the minus sign because dual logarithm, you know, I have to put this minus sign. And then we write here p, x, comma, y. And then we take a look at the concrete amplitudes x and y. Take the dual logarithm, x, comma, y, of x, comma, y. Okay. So this is always a capital. Yeah, that's just, I take a look at the probability mass function of the random variable x and y, yeah, of the joint random variable. And now we say where, here's enough place, yeah, where. And now we can say the joint probability px, comma y of x, comma y. This is just px of x times log 2 of py given x, y given x. So what's the probability of a certain combination of the values x and y? It's the probability of this concrete value x. And then sorry, this is nonsense. sorry. Multiplied, I just moved this to the left. I don't know why I've written this. So, and I multiply this by the probability of y given this x value. So this is, of course, the joint probability. And now we insert this in this equation here. So we can say, then this equation 1, let's say, is equal to minus, take a look at all values x. This is y here. Take a look at all values of y. And then I substitute this by px of x times py given x, so this conditional probability, times log 2 of, and now the question here, maybe you answer here, it's easier than from outside. If I insert this product here in the dual logarithm here, is it? The mouse doesn't work well. If I shift the mouse, I have to use this here. If you see the cursor, can you see the cursor? This is the joint probability, and now I substitute this joint probability by this product. So what happens here with the dual logarithm? What can I do? It's a sum. So, and therefore I start with this, okay, here is this px of s. So log 2 of px of x. Yeah? And then instead of writing here log 2 of this product, yeah, I write a sum. So I start a new sum, okay, and then I write here minus. I take a look at all x values, I take a look at all y values. Again, I write px of x times p of y given x. And then, of course, times log 2 of py given x, because you said you can write this as a sum, y given x. So now you see, what can we do? In this first sum here, we can say, here this depends only on x. This all only depends on x, not on y. So we can say, okay, I shift this to this point, and I also shift this to this point. Yeah? So let's start with this first equation. So I write here is equal to minus sum x, px of x, times log 2 px of x, times the sum of all y, py given x, x. Question is, let's say we would do this in red. What is this? So I have a concrete value x, lowercase x, yeah? A concrete value. And then I sum up all the probabilities of y given this x. What's the result? Let's say I have a 1, of course, because x has a certain value, and then I take a look at all possible values of y and sum up the probabilities of this y. For this x, it needs to be 1. So it basically means if you have a certain x and you could take a look in such a state diagram, that the sum of all outgoing probabilities on these errors needs to be 1. This is 1. So, and what is this? So h of x, this is the surprise in x, yeah? And then it's clear the next expression, we can say plus, or let's say we start with a minus sign, or let's say plus, yeah? Maybe this is better. Now I take a look at this expression. Again, I can put this px of x here in this first sum, yeah? Plus sum over all x, px of x, and then times sum, and I put this minus sign here. Looks a bit better now, yeah? And then I write here, I take a look at all y values, and then I have to insert the conditional probabilities. So px given y, y given x, times log 2 of, is the area, does it work? Second. here, see, second, so, no, this and this and this. How it works, hopefully. Okay, so chat. It's here. Log 2 of t y given x. Y given x. So then now it should be clear what we see here on the right-hand side. These are what you see here on the right-hand side. Yeah? These are conditional probabilities. So it means what we see here as an expression is, so now I lost my, here, okay. What you see here, including this minus sign, is h of y given x, right? Because it's a surprise. I consider all y values, the mouse doesn't work here with this. Yeah? I consider all y values, look here. And then I measure the surprise in y here for this given lowercase x value. And sum up all information contents of these possible y values weighted by the probabilities. So this means this is a surprise in y for a certain value x. And then I average these values for this concrete lowercase x values by the probability and end up with the conditional entropy h of y capital X, right? So this lowercase x means this is a concrete value, and this is basically now the random variable x here. And this is what we wanted to prove. Of course, we could do the same and say, okay, the joint entropy is of course the same as h of y plus h of x given y, but this is not so surprising. Yeah? So this is what I wanted to show. And now we can even proceed. Yes? Is there a question? But wait a second with this mouse here. I think you can see everything now. It works. Okay. Yeah. What is the question? Why is this one? Because the sum of all outgoing probabilities, you have a certain value of x. Yeah? And then you consider all values of y. Okay? And these values of y for this x have a certain probability. And the sum of all these probabilities, if you consider all y values, needs to be 1. It's a conditional probability. This one. I mean, now you talk about this one? This? Yeah, but here with this value, you weight these values because all these values here depend on x. They depend on x. I mean, this here you have px of x, but it's in this inner sum. You see? This h of y given x can be different for different lowercase x values. Therefore, even if the sum of all x values is of course 1, you weight something with this. And you weight the surprise, let's say, in y if you know x. But we discussed this in the seminar later. Yeah, further, there are more examples. We started with the seminar with such an example, and we proceed with this. Okay. And now we can take a look at the so-called chain rule of information. Yeah. And this is just, let's say, we further use this method. Yeah. Let's say this is, we denote this as chain rule, and this is known as chain rule of entropy. we just generalize this, what we've done until now. Why is it black now? I don't understand here this. I want to have a thick. Okay, again, blue, this, is it now? It's here, okay. We know that we have proven this, yeah, that h of x and y, the joint entropy is just the entropy of, let's say, x plus the conditional entropy of y given x. So now we consider, let us consider a three-dimensional. We consider this as a three-dimensional random variable. Let's say x, y, and let's say z also. Yeah, so we have three random variables, x, y, and z. And now we could say, we just put together, we say, we denote, for instance, v, yeah, as the two-dimensional random variable x and y, just as a trick. And then we know, because we know how to calculate the joint information, then we know h of, let's say, this v, yeah, and y, and z, sorry, yeah, and z. So we denote this. This is just v, okay? Now we take a look at the joint entropy of v and z. And this is, of course, the entropy in v plus the entropy in z given v. That's clear, right? And now we can say we know the entropy of v, where h of v is just h of x plus h of y given x. And therefore, we see that we can say h of x, comma, y, comma, z is nothing else than, and this is known as the chain rule, this is the entropy of x plus the surprise in y. What is uncertain in y? If we know x, plus the surprise in z, if we know x and y, and so on. And you, of course, you can expand this technique, yeah, which is denoted as chain rule, that the information grows from here to here by means of the conditional probability, from here to here by means of the conditional probability, conditional entropy, sorry. Because this is a conditional entropy, this is a conditional entropy. So here, yeah, you start with x, and then what's new is the info in y, if you know x. And here you say, what is the uncertainty in z if you know x and y? And this is how information grows. So you could say, for instance, let's say we take a look at x1, x2, x3, and x4, which could be, let's say, an excerpt of a data stream. So we say we have a source, yeah, which generates data. Okay? And we just take a look at the first 4 samples of this data. Yeah? And we say it's random, yeah, what comes out of this data source. Otherwise, we don't need to, let's say, transmit this also if it's not random, if there is no surprise. And then we want to measure the mutual information in this length 4 sequence. And then we could say h of, now, okay, I don't need to write, we get, okay, I write it again, but I can take a copy here. And then I write here just h of x1, x2, x3, and x4 is, of course, h of x1 plus h of x2 given x1, right? Plus h of x3 given x1 and x2. So this was before. Yeah? Plus h of x4 given x1, x2, x3. Okay. And later, if we talk about sources, it may happen, of course, yeah, that all these random variables here, x1, let's say this is an information source, yeah. And usually the sequence is much longer, of course. But you can have information sources where all these random variables here are statistically independent, right? And then we can say, in this case, the joint entropy is, of course, h of x1 plus h of x2 plus h of x3 plus h of x4. If they are statistically independent, there's no overlapping in these. If you take a look at the Venn diagram. And then you may have sources which are called Markov sources. And then you would get, for instance, for what is really denoted as a Markov chain or Markov source, that the joint entropy would be h of x1 plus h of x2 given x1. But then you say x3 only depends on x2 and not on x1. Yeah? Because the memory is only the past, one previous symbol, plus h of x4 given x3. So the memory is only one. Sometimes scientists say if the memory is larger, then I say it's a Markov source of higher order. Sometimes this is used. Okay. And now let's have a look at the final diagram, let's say, in this section. So this should be still section 2.2, joint entropy and conditional entropy. And then we end up this section with mutual information. Yeah, and this is just what you see as this area here in the Venn diagram, which is shared between, let's say, x and y. This is mutual information. And as I said, this mutual information will be used later to derive the information rate and the channel capacity of certain channels. So it's an important topic, but we don't want to discuss this here so extensively because we use it later. Let's say, just as a short diagram, yeah, if this is h of x, yeah, and let's say in another color, in red also, I use here, this can be, say, h of y. Yeah. And then this area here, I use now, let's say, again, here's black. Don't know the reason. Let's say this area, which is mutual to both, which is shared, this is denoted as the mutual information. So, and we use a different notation here. We use I of x semicolon y. Okay. But as I said, yeah, this is the mutual information. So the information which is contained both in x and y. Yeah. It's a common information basically. And but we can calculate a value for an example of this mutual information. Yeah. And later we are able to interpret this. So I do an example. So again, I don't have this thick. Understand here the concept exactly. Example. Let's say we have two random variables x. It can take the value 1 and 0, this random variable x, okay? And then we have a random variable y, let's say, and this also takes the values 0 and 1, okay? So let's say the probability of x equal to 0 is 1/2. The probability of x equal to 1 is also 1/2. And then we have here these conditional probabilities. Let's say if I draw here, arrow, yeah. This would be, of course, you know it, but I just write it again. This is Py of x, y given x, of 0 and 0, of course. Because, yeah, x is 0. What's the probability of y? Let's say this probability of y is just 1 minus Pe. And if this is 1 minus Pe, and I draw this arrow, what do I need to write here for this value? Pe. So let's say with a certain probability, yeah, if x is 0, then with a probability Pe, y is 1. And with a probability 1 minus Pe, y is 0. And possibly you may just think, oh, this looks like a channel, and we could interpret this as a so-called memoryless discrete channel. Yeah, and we could say we transmit information, binary information, by means of, let's say, binary modulation scheme. Yeah, so we assign continuous waveforms, yeah, to these zeros and ones, and then we receive an analog waveform. Yeah, if we transmit a separated symbol. And by means of sampling and threshold detection, we assign again 0 and 1. But in some cases, yeah, a 0 is received as a 1. And in some cases, a 0 is received as it was. So this E could be interpreted as an error probability. But we don't need to do this here. But we could say it's an error probability. And let's say this is 10 to the minus of 2 or so, yeah? So this means in most cases, a 0 is received as a 0. In 99% of all cases, in 1% there's an error. So it's wrongly received, but it's statistic. Yeah? And in this case, we would denote this as a so-called symmetrical binary channel, because it's symmetric. So I write again the same here. So a 1 may be for x, maybe also a 1 for y. If x is 1, then with a probability 1 minus Pe, y is also 1. Yeah? And then, of course, this is again this Pe in this direction. Okay. And now I ask you, or even Kazan or whatever, yeah? What's the probability that y is 0? What would you say? Because this channel is symmetric, what would you say? It's symmetric, yeah. The same things happen here for the zeros and ones. So what is it? It's still 1/2, of course, yeah. Yeah, because the outgoing branches here have exactly the same values. So this is 1/2 and 1/2. And now you see how to calculate this mutual information. You just see it in the diagram. How could we do this? Yeah. And one method would be, if you take a look at the, let's say, the red area. So the red area would be really this area. This is h of x. And you could say that the mutual information, yeah, this is our notation for mutual information, is just the red. So h of y minus what do I have to subtract? Yeah, very good, very good. This is this green area, yeah? So minus this conditional entropy h of y given x. Yeah? And later, if we talk about channels, okay, we denote this conditional entropy as irrelevance. Okay. Because let's assume it's a channel. Yeah? Let's assume it's a channel. Then, what's behind this? Let's say we know x. So you I'm the receiver, yeah, a detector, okay? And you tell me what has been transmitted. You say, X has been 1. And I have to take a look at Y and say, oh, oops, it's not 1, it's 0. So if there is a surprise in this Y, if I know the transmitter has generated a 1, there should be, in an error-free channel, there should be no surprise in this Y if I know the X. This is exactly the meaning of this irrelevance. It's irrelevant information added by the channel itself. Therefore, it's called irrelevant. So if this value is just 0, there's no surprise in this Y if I know this X, and then all the information which was available at the transmitter can be transmitted without any problem. Now we can calculate for this example this mutual information. Yeah, let's say this would be, again, I switch to blue. Yeah. Okay. Let's say h of Y is, of course, how large is it? If the probabilities are 1/2, it's of course 1 bit, right? Because log 2 of 2 is 1, and there's no question. And the other value is easy to calculate. It only depends on this error rate, or this value PE, right? Because we can say h of Y given X. Let's say I write this like in this equation. I can say this is 1/2, okay, because a 0 has a probability of 1/2 times h of Y if X is 0, okay, plus 1/2 h of Y if X is 1. And now we calculate where h of Y at X is 1. What is it? It only depends on these conditional probabilities. So it's minus PE log 2 of PE minus, so let's say this is here, yeah, we have this path, and now we consider this path. What is so I know X is 0, sorry. X is 0, yeah, and then, so this is a capital Y, of course, 1 minus PE log 2 of 1 minus PE, that's all, yeah. But we can say h of Y given that X is 1, what is it? It's the same value, because it's a so-called, if this would be a channel, it would be a symmetrical channel. So this is h of Y given X is 0. So then we see there's no difference. And since we weight both values, yeah, with 1/2, of course, we get is equal to, and then we just have to copy this here. So I do it. If the mouse would work, I would do this. So I just copy this, yeah. Control C, Control V, doesn't work. Control V. Next try. Control C, Control V. Oh, now the mouse is completely crashed, I guess. Doesn't work. Sorry, I write it here. Is equal to minus PE log 2 of PE minus 1 minus PE log 2 of 1 minus PE. Then we have the mutual information. We could draw a diagram, yeah, because we know h of Y is no, it doesn't work. Is 1 bit, yeah. This is 1 bit, and we have h of Y given X, and we have to subtract this value from 1 bit, and then we have it. And if this value would be 0, then the mutual information would be equal to basically 1 bit. So, and let's say, just to have a motivation for later, let's say we get now a value of 1/2 bit, half of a bit. Let's say, just for as an example, this mutual information here, this one, yeah, is just 1/2 bit. Could happen depending on this PE. Okay? So, what is the interpretation? Then we could say, if we transmit very long streams of this random variable x, denote this later as x1, x2, x3, and so on. Yeah? If we transmit very long streams, then statistically, if we transmit, this is only statistic, if we transmit 100 bits x, yeah, it's a bit at the transmitter, we could basically, among these 100 or 1000, let's say 1000 bits, there are 500 bits which can be detected without any error, error-free. The other 500 bits are not useless, they are used for error correction, to find and to locate an error, PE. So this is the so-called redundant information which I require. But we don't get this just without any effort. We need strong, powerful channel coding. So we have original information bits. Let's say we have statistically, just as this example, 500 information bits. And then we attend 500 redundant bits. So we have redundancy, but this is useful redundancy. And then we do this with a strong encoder, with a powerful encoding scheme. And then if the decoder works well, we can extract from the received bits, from all these bits, yeah, the original 500 information bits. And today there exists code, yeah, at least for the binary case, which are very close to this theoretical value, which is pre-described by this mutual information. So we have now these good codes. Yeah? For multi-level input signals, it's much more difficult, yeah, to approach this so-called channel capacity in practice. But nevertheless, the codes become better and better. And one reason is that we have more powerful signal processing available today, because the problem is always the decoder to do this. The encoding is quite simple. Yeah? And I will show you possibly in this lecture and in the next lecture, yeah, at least that encoding should work. Yeah? But the decoder complexity would be basically infinite, according to the ideas, the original ideas of Claude Shannon. Yeah, but now we have codes which work. Okay, so this is all for this section. Now we start with a new section. In this section, yes. This is, until now, we only talk about discrete channels, okay? And a discrete channel would be obtained from a waveform channel simply by doing demodulation, yeah, with binary detection. So let's say if you're familiar with modulation schemes, you could say, don't write it, yeah? So I represent, for instance, it's the simplest case, if I use a copper cable, let's say, I represent a binary 1 by a rectangular pulse, maybe by a sine wave with a finite length somehow, and represent, let's say, as a simple example, a 0-bit with a negative pulse. Yeah? So then we receive something. This is discussed in communications engineering. And then we receive, let's say, this, because it's noisy in the simplest case. Yeah? There's additive white Gaussian noise, and we receive noisy signals. And then we basically build or use an optimal detector just for these waveforms, yeah, by using a minimum distance criterion, yeah. And then with a certain probability, PE, we get an error in our decision, because then again, from this red waveform, we try to reconstruct the original information? Was it a 0 or was it a 1? Just from these pulses. Yeah, and the detector score we could use, for instance, a sampled matched filter to do this. Yeah. So then we receive zeros and ones, but sometimes in this case here, a 0 is received as a 1 and sometimes a 1 as a 0. But we transmit it with analog signals. Yeah? But we replace the continuous wave channel by a discrete channel. Because we represent binary zeros and ones with analog waveforms, and then we do the opposite basically at the detector. So, but this is later we also discuss continuous valued random variables, yeah, but we do this later. Yeah. I hope this, yeah. Okay, so now the next section is compression limits. So now basically we want to see, yeah, if we have a source, yeah, what can we do with this entropy information? You will see, for instance, if the source generates statistically independent symbols, all these symbols of a data stream are statistically independent, we need an average to encode such a symbol, on average, in the best case, a value which is equal to the entropy of this symbol. If the symbols are statistically dependent, yeah, we need less code word length, yeah, if they are statistically dependent, because in this case, our information grows slower from symbol to symbol. This is chain rule, basically. And now let's start. So this section is 3. And 3 is, as I said, compression limits. Just want to take a look. Okay, everything should be fine. I mean, I haven't switched on the video for Kazan, but I think if I switch on the video, this stuff really doesn't help, yeah, because I'm so tiny here on this video. You only see the upper part of my head, so I think I skip it. Yeah, it doesn't make sense. Yeah, this lecture hall. Okay, so I go back. Compression limits, and we start with, this is really important, and I think it's not so complicated to understand, because I have a few of nice slides. A law of large numbers. If you understand this, 3.1, you will understand 3.2 as well. Yeah. So when we consider an example, let's say example at a dice. Yeah. Example at 1 dice, and we consider the result as a random variable, let's say x, and x can take the values 1, 2, 3, 4, 5, and 6. And now we consider length 6 sequence of these outcomes, basically, of a dice throw. Yeah? And we denote the random variables of such a sequence as x1, x2, x3, and so on. Okay. Now let's consider length. This is just an example, yeah. 6 sequence. This has nothing to do here with that dice has 6 possible values. Yeah. A length 6 sequence. And the values could be, let's say, 2, 6, 5, 6, 1, 3. Yeah. This is just, you can use a computer, for instance, random generator, and it generates these 6 values. Yeah. And now we calculate for this sequence, this is a concrete sequence, yeah? We just calculate the arithmetic mean. What is the arithmetic mean? So we could calculate this for this example, concrete example, and I denote this as this x, yeah? And I use this abbreviation for an arithmetic mean. But to say how long is this averaging, basically on a horizontal scale, yeah? I use here a 6. I don't have this on the slides, by the way. If you take a look at the slides, I omitted here this number. But it's clear for an averaging, yeah? I have a certain length. I just want to show this is now 6. And then I have 1 by 6. And then I sum up all these values. I goes from 1 to 6. Yeah? And then I have here this lowercase xi. Because this is a concrete example. So this was a concrete sequence. You could also say this is a sequence. We usually use this, this kind of notation here in communications engineering. Yeah? And then we would say basically, let's say xi. And I goes from 1 to 6. And this is a concrete realization. So we have concrete xi values. Yeah? And if I do this for this example, what do I get? I get the sum of all these values. So 1 by 6. So 2 plus 6 plus 5 plus 6 plus 1 plus 3. Let's calculate this. This is 4, the last two. This is 10, 15, 21, 23, right? 23, if I'm not wrong, yeah? But, divided by 3. And this gives nearly 3.83, okay? And now it's interesting if we take a look at this value to compare this with the expected value of a dice throw. Expected value. But this is just an arithmetic mean, yeah? It's random, the result. If I make a new trial, I get a different value. Expected value is the expected value of our x. Yeah? We could also say we can write this as this, yeah? It's equal to the expected value of all these xi's. Yeah? I just use x as an abbreviation because all xi are. So now, since the result is random, I consider these dice throws, this sequence, yeah, as a sequence of random variables because the result is random. So in all random variables, I goes from 1 to 6 in these examples are identically distributed, yeah, are independent, identically distributed. I write this. Yeah. Have you seen this before, IID? Maybe, yeah. So this means there are independent. Yeah. So this is a sequence of dice throws, and it's a fair dice, let's say, yeah. And the next result has nothing to do with the previous. So they are independent. And all these x are identically identically distributed. What does it mean? They all have the same distribution. So the same probability mass function. Yeah, it's a dice. And this value is, of course, 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, because all have the same probability. Yeah? And then we end up with 3.5, I guess. Oh, yeah, 3.5. So you see there's a difference between this arithmetic value, arithmetic mean, over the 6 values and this value. Now it's an interesting aspect if we increase the length of our sequence and build this arithmetic mean, you will see we come closer and closer to this expected value. Okay, so we can say this this arithmetic mean can be modeled itself as a random variable because the result of summing up here is random. Okay, but now there is an interesting aspect. If we now take a look at the variance, we will see an interesting thing. So we could say, what happens with the variance? Variances. Let's start with the variance of the dice throw itself. Okay, so we could say variance. I write it like this, but you will understand what it is. Yeah, the variance is basically the AC power. Yeah, in our result. Take care. This is not physical power. It's the second moment of the centralized random variable. So we take our random variable, so this is the variance of x. Yeah? This is also valid for x1, x2, x3, it's clear. And this is nothing else than the expected value of x minus mx1. This is the same as, this is equals mx1, of course, the first moment. Yeah, the expected value is the first moment. So now we subtract the mean from the random variable and take a look at the power and average this, okay? So this is called variance, and this is nothing else than the standard derivation to the square. This is the variance. Yeah? You've seen this, I guess. So, and this is for this dice throw. If you calculate this, this is 2 point, nearly, it's not exact, yeah, 2.917. So now you may know, if I have two random variables, let's say x1 and x2, okay, and if I sum the results up, what happens with the expected value? I have two statistically independent, this is important, random variables x1 and x2. What happens with the expected value of the sum? What would you say? You even see it from the equations. It's the if you write expected value of x1 plus x2, yeah, it's the expected value of x1 plus the expected value of x2. And for the variance we get, for the variance, not for the second moment, we get the variance of the sum is the sum of the variances of the individual random variables. So we could say, if we first take a look at, now we take a look at basically such an arithmetic mean, which is random, as we have seen. Now we take a look, not directly as an arithmetic mean in order to show you, to simplify the result. We first take a look at this sum here. So we sum up from I equal to 1, let's say to capital M, not to 6, just this stands for 600, 1,000, whatever, yeah? So we use capital M dice throws basically, yeah, and sum up the results. And take a look at the variance of this result. And this is just m times the individual variance, which is m times sigma x squared. So this is basically the AC power increases with the number of random variables, proportional. But now, very interesting, maybe you see the result, you can answer. What happens with the variance of our arithmetic mean? So again, variance of. And there's now a slight difference. 1 by m, yeah, times sum, I goes from 1 to capital M, xi. Now let's remember here the variance is the expected value of the squared zero mean random variable. So we have to square the expression. Okay, and what do you see? Think what's the result here? So it's, of course, it depends on sigma x squared, of course. But what do you say? What happens now? If I square all the values here, expected value from the square, and here I weight every value with 1 by m, then it's 1 by m, exactly. And this is really interesting, because if we increase the number m, which means the length of our sequence, we decrease the variance of our arithmetic mean. So this means when we say, we denote this, so in other words, yeah, if I repeat this for this dice, let's say with 1,000 results, 1,000 dice throws, the result would be much, much closer to 3.5. Yeah, it's absolutely unlikely that the result is still, let's say, 3.81 or so. We see this in the picture then. And then we say, and this is the so-called law of large numbers, that for large, so now we see, yeah, if we sum up these values of this random variable, okay, the expected value is the sum of all expected values. But if I divide by m, of course, the expected value of the arithmetic mean is 3.5. There's no question. This is the expected value. And the variance becomes lower and lower and lower if I increase this m. So I can be sure that if I make a trial, the result is random, but it's absolutely close to this expected value of our random variable. And then we say for large m, we say that the arithmetic mean of our x, which is the same as, now I skip this m, yeah, as the sum of, 1 by m, sum I goes from 1 to capital M, xi. So I take a look at the arithmetic mean of a sequence of random variables, and this converges in probability to the expected value of x. Where I say the expected value of x is the same as the expected value of each xi. It's just an abbreviation, because we have identically distributed random variables. They all have the same distribution. Yeah? And that's interesting. And this is, I mean, you would expect this probably. Yeah? And we can take a look at the picture on the slides where you see this. Yeah? And I used just MATLAB or Octave, doesn't matter. Yeah? This is a program which is available. And you can use this to generate such numerical results, let's say. You see it here. It's here. Here you have again the equations, whatever. Yeah. The results are shown here. I make it a little bit larger. So let's say we start with this arithmetic mean here, yeah, of this dice throw. And here we have the sequence length. And what is shown in blue is this arithmetic mean, depending on the sequence length. And then we see at the beginning we have a large variation, of course, yeah, because the sequence length is short. And then if we increase the sequence length, we come closer and closer and closer to this expected value. So we sum up the values, the results, and divide by the length. And we can even prove this by means of histograms. What I've shown here is, this is this arithmetic mean, which was shown here. It's the arithmetic mean on the y-axis. And this is just here. It's the arithmetic mean on this x. And here's the probability of this arithmetic mean for a sequence length of 1,000. And I repeated the experiment 100,000 times. So I need to do this to get a histogram. So the sequence length is always 1,000. So I used MATLAB, generate numbers between 1 and 6. All have the same probability. All are statistically independent. Yeah. And then I built a histogram and said, As you can see, on average, the value is 0.5, but this is not astonishing. Yeah? And then sometimes the value is larger, sometimes it's closer, or it's lower than this 3.5. And here you see the histogram. But you can also see values, let's say, which are much larger than 3.6 and a bit more, yeah, are quite seldom. And values which are lower than this value here, 3.38 or so, also have a very low probability. And now I repeated this experiment with a higher sequence length, let's say 10,000. And then it looks like this. You see, there are almost no cases for this sequence length of 10,000. It's longer. And there are always no cases where the arithmetic mean is larger than, let's say, this is 3.5, this is 3.6, so this would be 3.55 or so. Yeah. So the result is always very, very close to this expected value. And in almost no cases, yeah, the result is, let's say, larger or equal than 3.6 or 3.4. And this can be proven that this is a law, yeah, by means of this variance, because the variance of our arithmetic mean becomes lower and lower and lower if we increase this m. Yeah? And you can see this even from the statistics. I've shown here the probability, cumulative probability density function, cumulative probability density function of a dice throw, and you see, okay, you have the result 1, 2, 3, 4, 5, 6, yeah, and a value lower or equal than 6 is the probability is 1, and so on. You understand, yeah? And then I took the same for a length of 10,000 sequence and plotted the cumulative distribution function of the result. And you see almost all the cases are very close to, or the results are very close to 3.5. Because first I have a certain distribution, it's equally distributed, dice roll, yeah? The result equally distributed between 1 and 6. And then I get new distributions, because if I sum up two results and divide by the number, I get more possible values, of course. Yeah. So, and if you add two random variables, and if they are statistically independent, you need to do a convolution of the probability mass functions. So the probability mass function, if I would sum up 10,000 equally distributed probability mass functions, which look like an equal distribution, yeah, then it looks more or less like a Gaussian distribution. But then I divide the result by m, and the width of this Gaussian distribution is quite small. The average value is 3.5, and the variance is very low, because the variance decreases with m. Okay? Now, we have all the tools to do this, to measure the arithmetic mean of the information content. We don't need to know new things, because we understood, hopefully, the law of large numbers. Yeah? That this arithmetic mean converges in probability to the expected value of the random variable. You see it on the diagrams. And now I do basically the same, and then rewrite it down. We write the equations more or less as they are here. Now I do the same. Let's say I have an example, yeah, and I have a discrete source, yeah, which generates 4 symbols. Let's say A, B, C, D, or let's say the values 1, 2, 3, 4. 4 values. But these 4 values have different probabilities, so that the entropy of this random variable, which can take the 4 values, it's not 2-bit. 4 values, if we would have equally distributed values, yeah, the same probability, we would have 4, yeah, the probability is 1 by 2 if there would be equally distributed, 1 by 4. So the entropy would be 2-bit if we have such an equally distributed random variable. But here it's only 1.75-bit. And now we measure the arithmetic mean of the information content of a long sequence. And you see, if we increase the sequence length, the mean, the arithmetic mean of a concrete sequence is close to this entropy. This is just described by the law of large numbers, as we've seen before, because the information content of a concrete sequence is again random. And we have to do exactly the same what we have done before, but the new random variable, instead of what we called here x, you have the information content, okay? And I have shown again here a histogram. You can take a look if you're at home, yeah? You take a look and say, oh, what's shown here, and then you will understand. But it's, again, it's a histogram. And then I show here the concrete arithmetic mean, yeah, of this information content of the of a long sequence. So, and we get different results for this arithmetic mean of the information content. We get different results. The histogram again uses 100,000 realizations. So I repeat this experiment 100,000 times in order to build a histogram, to make a statistic. And then I say, what is this arithmetic mean? And you see, in most cases, it's more or less exactly this 1.75. And in almost no cases, yeah, it's larger than, let's say, 1.77. So there are no cases where this arithmetic mean, yeah, is quite different from this entropy of our random variable. This is interesting because if we understand this concept, we know that we need only in this example, 1.75 bits to encode, statistically to encode, yeah, an original symbol. We will see from this example. And we can now basically write down a bit, understand this. So now this property or this
Hello.
yeah, what we get is denoted as asymptotic equipartition property. Yeah, this is
Sir, I have a doubt.
The law of large numbers, but for the information content. No. So 3.2 asymptotic, and we need this again to understand the channel capacity. Otherwise, or mutual information. Yeah, otherwise it would be impossible. This is really an original work, yeah.
Hello.
Describing the original work of Claude Shannon from 1948. So asymptotic, equipartition, property. Okay. So now we use this, yeah, to find the compression limit. I mean, the title of section 3 is compression limits, yeah, to find the compression limit, but also later to derive the channel capacity of a certain channel. Yeah. So now we assume, or we measure the arithmetic mean as before. What's this? Kommentaranfrage. Möchte freigegeben Inhalte kommentieren. Möchte die freigegebenen Inhalte kommentieren. Let's say what happens. I write here. Yes?
Sir, I have a doubt. Can you hear me?
Professor Wolf, I have a doubt. Okay.
Hello.
What is your doubt?
Sir, is my voice audible? Hello.
What happens now?
I think he is not listening. Try writing in the chat.
So there is Mr. Sharma and he has a doubt, but I don't know what happens now. Maybe you can talk? Okay, then we need to proceed. Kommentar starten. But I don't see a comment, and he is asking, but I don't understand. Sorry. I don't hear him, and I don't know what to do to make him tone me PC video tone. I think Videokonferenz Teilnehmer. I don't hear anything. Are you speaking?
Hello. Hello. Sir, is my voice audible?
Oh, wait. It's so loud. Wait, one
Okay.
second. Okay.
Okay.
So
Uh,
now you. Okay.
yeah.
Maybe you increase the distance to your microphone. Sorry. Otherwise.
Okay.
Yeah. Okay.
Sorry. Now is it okay, sir?
Yeah, it's fine. Yeah. Okay.
Yeah. Sir, I would like to know how did you got that variance in the first step? Like you calculated variance of x, which is expectation of x minus mean, which is
Okay.
nothing but sigma x square. So you have mentioned
I understand
2.917.
the question. I
Yeah.
understand the question. Maybe now you switch off your microphone. Maybe, maybe I calculated a wrong result. Yeah, but the approach would be the following. Yeah, I mean there are two approaches to get this value, 2.91. Okay, there are two. Well, but now it's interesting what I need to do because now this is a surprise. I just switch off this and now I can write again. There are two possibilities to get this value, let's say. One is your question is why is the variance 2.917, right? Is this the question?
Yes, sir.
Yeah, it's quite simple. There are two possibilities, and maybe if you have a calculator, you can do this or you can check it. Yeah. One possibility is, I can write. That's nice. That I say the expected value of, x squared. This is just 1 plus 4 plus, this is 2 squared, right? 9 plus 15, 16, it's 4, yeah, plus 25 plus 36 divided by 6. So this is the total power, what we denote as total power, or the second moment, yeah? I don't know exactly what comes out. Maybe we can calculate it. So this would be 20, 29, 30, right? 50, 55, 85, 91. So this is 91 by 6. Yeah, okay. And now you just have to calculate. You can check it if you have a calculator. Yeah, or I don't know. Maybe I have also a calculator here on the computer.
It comes out to be sir 15.16.
Yeah, wait. And now we calculate. Then this is just this second moment here, mx2. This is mx2 minus mx1 to the square. So, and I don't, maybe this is wrong with this 2.9, then I'm sorry, yeah, but the rest is correct, that we decrease the variance. So what we get is basically this, this value, yeah, minus 3.5 to the square. And what comes out, maybe you can calculate this. This is the shortest way to obtain this result. Yeah. I can check if I have here such a calculator. I never use Windows, that's the problem. Calculator, is there a calculator? Bildschirmfarben. 2.966. 9166, then it's correct. So sorry for your comment, it was correct. Okay.
Sir, I just wanted to know how it came. I was not doubting your answer. I was just asking how we came to that answer. Yeah. Now it's clear to me.
Now you can
Now it's
see.
clear.
Yeah, but you can
Yeah.
also, but you can also use a different method. Yeah, you can
Okay.
say before I instead of summing up the squares of the results, I can also sum up the squares of the results minus 3.5, and then you end up with exactly the same result. So you square 1 minus 3.5 to the square. Yeah. 2 minus 3.5 to the square, and so on, divide by 6, you get the same result. I showed this in a seminar later. Yeah? That always the second moment here plus the variance is equal, the second moment of the, that the second moment is basically the AC power plus the DC power. Yeah? So AC variance plus first moment to the square gives total power. This is always true. This is the shortest method to find this variance. Okay. So I'm happy that this was not a doubt, this was just a question. Okay. So now we measure the arithmetic mean. At least we now know that your microphones work. We can hear you. The arithmetic mean of the information content of a length M sequence. Of independent, identically distributed random variables xi. Okay, I think you understand. IID independent, so they are statistically independent. They all have the same distribution. That is, P xi of x. So if you take a look at the probability mass function of a certain random variable in this stream of random variables, yeah, it's always the same. So this is px, let's say j of x, yeah, for any j, and this is equal to, we just write px of x as an abbreviation. Yeah. This is our probability mass function. There is only one. Let's say we just define example. We say we have px of, let's say, a. Yeah? A stands for a certain number. It's a random variable. And this is just 1/2. Px of b is just 1/4. Assume that this b is just a certain number. It's countable. Px of c is just 1/8. Px of d is also 1/8. Yeah? So we have basically a xi. Yeah? All the random variables have an alphabet, yeah, which is A, E, C, or D. So it can take the values A, B, C, and D. And here we have the probabilities. Here we have the probabilities of these states. And this means, in this example, yeah, we could say h of x is equal to h of, let's say, xi, yeah? Independently on this, for all i's, we get the same entropy because they have the same statistic. And this is just, what is it? 1/2 times 1. Yeah, this is the information content of, we generate an A. If we generate a B, we have an information content of 2. So times 1/4 times 2 plus, and the other symbols have an information content of 3 bits, and they have together a probability of 1/4. So it's this, yeah. What comes out is this, which I used this in the example on the slides, 1.74 bit, let's say, per symbol. Yeah, I write here per symbol to say on average. But you can also skip this per symbol if you want. It's just bit. So both are artificial units. And now we consider a concrete sequence. Okay? As we considered a concrete sequence for the dice. Now consider the sequence. Let's say, I could say 6, but now I said the length is m equal to 10 sequence. So it could look like this. You write here, let's say I, this is this index, yeah, and I goes from 1, 2, 3, 4, 5, 6, 7, 10. Again, this is a quite short sequence. And in order that we see later that this arithmetic mean of the information content is nearly equal to the entropy, we have to use much larger values for this m. Now, this is just random. I use this lowercase x, okay, xi, because it's a concrete value. And this could be A, B, C, A, D, B. If we repeat this experiment, we get different numbers. We get a different sequence because the result is random. Yeah? And now we say, okay, what's the probability? Px of these concrete values xi. So this is 1/2. The probability of a B is 1/4. The probability of an A is 1/2, 1/2. The probability of a C is 1/8. The probability of an 8 is 1/A is 1/2, 1/2, 1/4, 1/8, 1/4, right? And now we measure here the information content of this concrete value, which depends on the probability of this value. So, you know this is log 2. Let's say I write this in order to skip the minus sign, Px xi. There's not enough place for the, here I can move this a little bit to the left. So, this is in bit, information content. So the first symbol has an information content of, say I write this in red, 1. The next 2, the next 1, the next 1, 3, 1, 1, 2, 3, 2, right? These are the information contents. Now if I calculate the mean information content I get for this concrete sequence, I get, let's say, I10 is equal to 1/10, and then 1 + 2 + 1 + 1 + 3, 1 + 1 + 2 + 3 + 2, divided by 10, arithmetic mean. Yeah? And then the result, it's, let's say, 1.7 bit. And you see again a difference. Yeah? It's 1.7 bit. And if I repeat this, a new trial, I get a different result because it's random. So we can write the result is random. And we can model the arithmetic mean. Again, as a random variable. Maybe there's just the time to write down the following. If I say, what is the information content of this random variable? I just want to show this is not now a concrete value. I insert a random variable, thus a function of a random variable. I just calculate a number of a random variable. It's still a random variable. So this, what I wrote here, is a random variable, a new random variable. Say y of xi or I. Yeah, it's a new random variable. This is minus log 2 px of xi. Just use these capital letters to say, now I want to show that the result is random of this. Now, this is a sequence of random variables. If I now calculate that this is information content, if I now calculate the arithmetic mean, now I take a look at the arithmetic mean. Let's say I take a look at capital M values and again write 1 by m. I sum up, I starts at 1 to capital M. Sorry for this short delay, yeah, but I finish in a few seconds. Xi, and this is the same as, let's say, 1 by m. Sum I starts with 1, goes to m, then this minus, yeah, from log 2 px of xi. Yeah, but this is random. This is a random number. But for large m, yeah, the variance of this result becomes lower and lower and lower. And again, it converges in probability to the average value of this, to the expected value of the information content. And this is just the entropy. So for large m, this is already our result, and we can use this result to show important properties for large m. Get again 1 by m times 1 from 1 to capital M minus sign just from this log 2 x of xi, capital Xi. This converges in probability to the expected value of minus log 2, because this is our random variable now, minus log 2 of x of xi. Yeah? But this is just what we denote as the expected value of the information content. Yeah? This is the information content of a random variable. The expected value is just entropy. And this is what you have seen on the figures. I think you remember. And what you see now, and we will basically finish this in the next lecture. What you see here, if you take a look at the left-hand side, and this is nearly equal to this expression, we can extract the probabilities of these sequences. And all these sequences have the same probability. And the probability of these sequences is nearly 1 by 2 to the power of m times h of x. They all have the same probability. So there are so-called typical sequences. All have the same probability. Since there are these typical sequences which all have the same probability, I need the number of bits to encode them. You see, on average, even there are non-typical sequences which have a huge, let's say, derivation from this arithmetic mean. But even if I encode these sequences too, on average, I nearly need only a value of h of x, so the entropy, to encode a single symbol. This is the law of large numbers. But we proceed in the next lecture. So thank you. And yeah, we see us in the stay, I guess. Thank you. Okay, bye.
Thank you, Professor.
day. Day.
Goodbye.
Bye-bye. So I put this again in the internet, of course. Yeah. Jetzt über der Zeitdruck.